instead of actually increasing the temperature of the surroundings. So all the energy is just going into breaking those intermolecular forces. So melting, or fusion, this is our first state change, or solid to liquid one. That's an endothermic process, meaning it takes in heat. Absorbed energy is utilized to reduce the intermolecular forces. This is called heat of fusion, don't worry too much about that. But here, all this energy is being added to break all the intermolecular forces that are keeping a compound as a solid, so it can successfully turn into a liquid. Particles eventually move more freely, with less intermolecular forces once they become a liquid. So here is our melting point. We call the flat area on these temperature charts, on these phase diagrams, as the melting point. So that's the temperature which this will actually melt at. So literally every single compound has a melting point, its own individual, specific, and unique temperature in which it will melt. And energy is added all along here. Then once we get to the end, all particles are freed from their intermolecular forces, and then they can just go hang out and be a liquid. So melting point is a characteristic property and can be used to identify substances. And the way you find melting point is looking for the flat part on the graph between the solid and the liquid. So the greater the attraction between particles, the more energy is needed to overcome the intermolecular forces. This is something kind of interesting. So this is CH4, methane gas. It is not, don't worry about the polarity too much right now, but here the methane gas has very weak bonds between it, so it takes a much lower temperature to turn it into a liquid or a gas. Think about how oxygen, for instance, or like nitrogen is a gas at room temperature, like right, the air around us, versus some things aren't a gas, like sodium chloride, until insanely high temperatures. Like imagine trying to melt salt and then turn it into a gas. That's an ionic one with a big charge and a big attraction. That takes a ton of energy. Like think about turning sodium chloride or like a block of metal into a gas. It's just like insane to even think about. But that you'd have to get like to thousands and thousands of degrees there. Whereas things like methane or like carbon dioxide or whatever have weaker bonds between them, so they are able to become a gas even at like 20 degrees Celsius or even negative, like in the negatives, like right, like when it's cold in the winter, if the air doesn't turn into a liquid, it's still gaseous, and that's because it has less attraction between its molecules. So that's something to keep in mind, is that like a weak intermolecular force means something will turn into a gas easier, or turn into a liquid easier, and a stronger one means it wants to stay solid more. Here's our next one, vaporization, liquid to gas. This is very similar to melting, except our plateau is between liquid and gas now instead of solid and liquid. So again, endothermic, and energy is used to further reduce the intermolecular forces, that's our heat of vaporization, and particles eventually move unrestricted as a gas. So vapor is a liquid that has changed to a gas, and gas is the substance normally found in the state. That's just sort of a definition thing. But if we boil water till it turns into a gas, it would be called water vapor. Whereas something like propane, we'd call it gas because it's normally a gas as we find it. So vapor just means something that we've like heated up to change into a gas. That's an important little distinction there. So here, again, we're adding our energy and absorbing it, absorbing it, absorbing it, absorbing it, absorbing it all across this plateau, which we call the boiling point, until all particles are freed. And boiling point, this temperature right here, again, is a characteristic property that can identify things and compounds because they all have a unique boiling point. There are two types of vaporization. There's boiling, in which liquid particles at the bottom are given enough energy to overcome intermolecular forces and vapor is created, and evaporation is when liquid particles on the surface have enough energy to overcome intermolecular forces. So evaporation just kind of happens without us doing anything, whereas boiling we have to add heat. Obviously when you have a kettle of water, if you boil it, it's going to turn into a gas faster than if you just let it naturally evaporate. So evaporation and boiling are the two types. What you need to know there is that evaporation is on the surface, and boiling really comes from the bottom. Here's just like an image again. Boiling is the rapid vaporization of a liquid, meaning you're rapidly turning it into a gas. Energized particles near the heat source spread out, forming bubbles that rise and enter the atmosphere. So we have here we have a vapor pressure above in the atmosphere. Again, don't worry too much about these definitions just now, I'm just trying to give a visual. But in boiling, we get bubbles forming inside a liquid, which get more energy than the force pushing down on them from the atmosphere, so they can escape. Whereas evaporation is just little surface ones going off as they can. It's much slower. And then boiling point, as an important definition, is the point where vapor pressure produced equals air pressure, and that the liquid bubbles are able to escape as a gas and change state. So we looked at a heating curve. A cooling curve is the exact same thing in the other direction. So imagine you're starting as a gas here and you're lowering the temperature over time. This is just like a flip, if you imagine this flipped of a heating curve, where we're going to cool stuff down. So we still have like a gas here. We have a plateau to indicate our phase change, and this is still at the boiling point. Then we turn into a liquid until we get back to our melting point or freezing point. They're the same thing. And then become a solid again. So in a cooling curve, particles lose energy and are pulled together by their intermolecular forces. The energy released as particles condense and freeze into more restrictive phases, and it's exothermic, and the temperature still plateaus at the same area. So think of magnets coming together now. Instead of pulling them apart, think about you have two magnets and they really want to come together, and you let them go and you feel that release of energy when they come together and that snap. That's what we're looking at here. So the first one is condensation, or liquefaction you might see, but we're going to call it condensation. Particles slow as the kinetic energy is lost, and the energy released as intermolecular force takes hold and restricts movement. So energy gets given away in movement and gets taken up as the force that's holding the molecules together. So you may remember, as we've told you many times in science, that energy can't be created or destroyed, but it can be changed. So here we're changing the energy of movement into an energy of attraction. Again, condensation occurs at the same temperature as the boiling point, and so let's take one more look there. So we're going from gas, we're losing kinetic energy and releasing it until all particles become recaptured by their intermolecular forces. Then they turn back into a liquid as we remove more and more energy. Freezing or solidification. This is the opposite of melting now. So particles continue to slow as more energy is lost. The intermolecular forces strengthen even further than a liquid and restrict a crystalline such amorphous structure that we talked about last week. And it's exothermic, so we're losing energy until all particles become solid in the structure. So that's what freezing is, and again, we're looking for these flat points on the graph. And that's our melting point. And yeah, freezing occurs at the same temperature as the melting point, and boiling and condensation occur at the same temperature as well. Then these are just like the fancy ones between solid and gas. Sublimation is the direct phase change between solid to vapor, so that's going to take energy in. We see it here. So that's an endothermic one, whereas deposition is the opposite. It's a direct phase transition of a substance from vapor to solid without going to liquid, and that is exothermic. So these are rare phase changes that happen with like very specific pressures. It's important to know of them, but you don't see them nearly as much as the normal, like these ones. So here's two questions that I'm just going to pose to you before we end off today's lesson. I know it's been a ton of information, but just feel free to rewatch this and use it as a reference, read it over, and also check out the handout from the booklet. This is just meant to be a little crash course on phase changes to go along with everything else. But with that in mind, let's look at this question, and I'm going to invite you to pause your video and try to answer this in your head, and then we'll pull up the answers in a second here. But it says below are two different heating curves. A, what is the freezing point of these two substances? And B, predict which substance has the strongest intermolecular force. So, I'll give you a second here. 5, 4, 3, 2, try to take a crack at it. I'll give you another second to pause it. And we are back. So, here are our melting points, 17 and 0 degrees Celsius. They are the flat temperature where we go from solid to liquid, and that's a type of question you'll see here is like, what's the melting point, what's the boiling point, things like that. If I was going to ask you what state is it at number 3 here, you should be able to say liquid because it's at between the melting point and the boiling point, so it's going to be a liquid in here. Then the strongest intermolecular forces are the first substance, because it takes more temperature to make it melt and make it boil. It's at 17 and 115 instead of 0 and 100, which means that it has a stronger force holding it together. So anyways, chemists, I hope this video helped you get an understanding of phase changes. Feel free to email me at mrbscienceMD@gmail.com with any questions, and keep up with all the other stuff that's posted. Hope you have a lovely day.